We've previously looked at work during the reversible expansion and compression of gases. So the other side to the equation for how the energy changes during this process will be the heat. So we have, for an ideal gas, that we know that the energy, the internal energy U, is going to be some prefactor here. For a monatomic gas, it's 3/2. For diatomic, 5/2. Nonlinear polyatomic would be 6/2, or 3 times nRT, which we know is also equal to number of particles times Boltzmann constant times temperature. But the point being that if we have a constant number of particles, then the only other state variable that the energy depends on is T. So if we have at constant number of particles, we have that the change in the energy for a system would be directly proportional to the change in the temperature. So this means that if we have the temperature change being 0, so if temperature changes 0, then change in the internal energy is going to be 0. So when we have the change in the temperature being 0 during a process, this is referred to as an isothermal process. So iso, same, thermal, you can think about it being temperature. So same temperature during a process, isothermal process. So when we used the ideal gas law to derive what the expansion and compression work is in a reversible expansion or compression in the previous video, we looked at the ideal gas law and we said that it was PV equals nRT, and then we derived that the pressure at any point along the compression or the expansion of the external environment was nRT over V. And we assumed during that T was going to be constant. So we assumed that the delta T, the change in temperature, was going to be 0. So we have kind of implicitly assumed there that we were talking about, for those expansion and compression processes, that we had a reversible. So we talked about reversible and isothermal compression or expansion. So that expansion or compression event was not only reversible, it was also assumed to be isothermal. Okay, so we know from our conservation of energy for a closed system that the change in energy has to come from somewhere. We can't create or destroy the energy. And it has to be the heat plus the work, Q plus W. And we know from it being isothermal that the change in temperature was 0, and therefore if the change in temperature is 0, the change in energy is also 0 because it's proportional to that. So delta U is going to equal 0. So that means 0 is our heat plus work. So our heat is just going to be minus work. It's going to be the opposite of work. Whatever energy we take in or release from work, we have to release or take in the opposite of that in heat in order to keep the temperature the same. So we said that our work for such a reversible isothermal process was minus nRT log final volume over initial volume. So work, heat has to be the opposite of that work, so negative times negative gives us a positive. So that means for our reversible isothermal processes, we have the heat, which must be input to keep it isothermal, is going to be positive nRT log V final over V initial. All of that work has to be canceled out exactly and equally at all points along the process by a corresponding input or release of heat.